Can I achieve a grade 7 in a GCSE Physics exam, but without writing a single sentence or using a calculator? For this challenge, I went over to GCSEPhysicsOnline.com. I looked at the past papers and I chose one from OCR completely at random. And this one here has topics which are going to be familiar for anybody doing GCSE Physics. Now, the grade boundaries for this paper meant that you needed to get 52 marks out of 90 in order to get a grade 7, which is a really good pass. But I was wondering how many marks are available if you don't do any of the longer written explanations. So with that in mind, let's see how I get on. Now I've got a counter up here that's going to count up the marks. I want to try and get to 52 as I go through the paper. And again, I'm not going to be writing any sentences. I'm not going to be using a calculator at all. So if you want to see how I get on, just keep watching the video. So the first one is actually a multiple choice. In actual fact, section A on this paper is all multiple choice questions. So let's just whiz through them. The first one is about how models have changed over time. And the atomic model has changed because older models could not explain new evidence. So the answer is C for my first point. We then have a calculation with a circuit. We want to know the current, and we know that's going to be equal to V over R. And here, the voltage in that circuit is 15 volts, and the total resistance is going to be 10 plus 10 plus 10, which is 30. So 15 over 30 is just a half, which is 0.5 amps. So the answer is A for our second mark. No calculators needed, and actually less than a minute for each of those questions. We then have a question about fluid under pressure. And if we think about what's going on as that's compressed, there's going to be a force acting outwards. I'm just going to draw these arrows, but basically the fluid everywhere is going to be at the same pressure, and these are all going to be at 90 degrees. So the force is at 90 degrees to all points on the surface of the fluid, so D is the correct answer. We then have a question about moments. We've got a force of 400 newtons, and this is going to be acting clockwise about that pivot, and the moment is equal to the force times that perpendicular distance. Sometimes we can also write that as F times S. So that's going to be equal to 400 multiplied by 0.8, and therefore that's going to be less than 400, so that's going to be 320, and that's going to be Newton meters. In this case it's clockwise, so here the answer must be B. So again, our fourth mark in less than 4 minutes, which is what you want to be aiming for as you're doing past papers. What influences whether an object floats or sinks? Well, it's really about the relative densities of those two objects, and therefore 5, the answer is D. We then have a student of weight W going up some stairs. What is the work done against gravity? So that's the key thing, we're going against gravity, and therefore the work done is going to be equal to the force multiplied by the distance in the direction of that force. So the work done is going to be equal to the force down, which is their weight, multiplied by their vertical distance, h. And therefore, WH is the correct one for B. Just be aware that we use W to represent weight and W to represent work done. Okay, so I think we're doing all right so far, 6 marks. We then have a wire inside a magnetic field. Now, the longest part of that cell is a positive end, and conventional current goes positive to negative. So I'm going to put an arrow to show the direction that's going. So that's the direction of that current in the wire. But the magnetic field lines go from north to south. So using my left hand, I'm going to line up my first finger with the magnetic field, my second finger with conventional current, and now my thumb is pointing down, which would be the motion of that wire. So the answer is A, downwards. Next up, we have a transformer. This is a step up because we step up the number of turns, and therefore we step up the potential difference. So it's going to be higher than 2 volts. And we know that the ratio of the turns on the primary to the secondary is the same as the ratio of the voltage or potential difference on the primary to the secondary. And therefore we can say that 50 over 250 is equal to 2 over Vs. So that goes up by 5. That's going to go up by 5 from 2 up till 10. And therefore the answer is D, because 2 over 10 is the same as 50 over 250. Not too bad so far. I know we're going quickly, but I just want to kind of get through this to see how many marks we can get. We now have a velocity time graph. We want to look at the distance travelled, or the displacement, and that's going to be equal to the area underneath that line. So here we've got a triangle. So the distance travelled is going to be 1/2 times the base, which is 5, times the height, which is 8. So that's the same as 1/2 times 40, which is just equal to 20. And therefore the distance travelled, C, is 20 metres. What's equivalent to the mass of an object? So we've got ratios of acceleration to force. I'm going to say that F equals ma, Newton's second law, and say that m is equal to F over a. So I've just rearranged that equation to say that mass is equal to the ratio of the force to the acceleration, which is b. So b is correct for number 10. Still no sentences, just a few equations. What does not increase the magnetic effect of a solenoid? So this coil of wire with a current going through it is going to be a magnetic field around it. If you increase the current, the magnetic field gets stronger. If you increase the number of turns, it gets stronger. If you put a soft iron core in the middle, we make it to a really strong electromagnet. So B, C and D make it stronger, but increasing the cross-sectional area doesn't make it stronger. So the answer for 11 is A. We then have two cars coming towards each other. What velocity does the driver of car Q see car P coming towards them? Well, they're going at 25 that direction. They're coming at 15. So they appear to be coming at 25 plus 15, which is equal to 40 metres per second coming towards them. So the relative speed of approach is 40 metres per second. We then have a graph to show a bouncing ball. Now the ball is going to be bouncing maybe off a desk or off the floor. So the height can't go below 0. So it can't be this one or this one. Now it can't be D because this always has a positive velocity. So that maybe be something moving and then moving and moving in the same direction. So it's not D. In actual fact, the answer is B. And basically we can see how the velocity gets smaller, maybe as something is going into the air, till it gets to the top where the velocity is 0. And then the velocity changes direction, so it's now negative compared to the positive value it had previously. And so B is an appropriate answer. For 14, because that system is in equilibrium, so it's balanced, we can say that the clockwise and anti-clockwise moments are equal. The clockwise moment is going to be provided by the effort, I'm going to call that E, times the distance of 1.2. And that's equal to the weight down of 300 times 0.4. So we could also say then that the effort is equal to 300 times 0.4 over 1.2. But of course 0.4 divided by 1.2 is a third. So that's equal to 300 times a third, and that's just equal to 100 newtons. So the answer for 14 is A. Okay, and then 15, we've got wire, we've got different forces, currents and a length. That means you should remember that F equals BIL, or B, the magnetic field strength or magnetic flux density, is equal to F over IL. Now for all of these, the length is the same, and therefore we can say that the magnetic field strength is proportional to F over I. So for this one, I'm just going to put another column on the end. We've got the force divided by the current, and so 2 divided by 0.1 is 20. 2 divided by 0.2 is 10. 4 divided by 0.1 is 40. And 4 divided by 0.4 is 10. So the biggest ratio of force to current is C, and therefore the answer for that is C, because that would then have the biggest magnetic field strength. So just whizzing through those, 15 marks available so far. That should normally take you less than 15 minutes because you want to be going for less than 1 minute per mark in your exams. And that gives you plenty of time to check through your answers and to make sure at the end that you've made no silly mistakes, you haven't missed any questions out. But of course, this paper is out of 90, and that means there are 75 more marks available. So now let's have a look at section B. So this is where it gets really challenging. The first bit then, what's the name of that component? So this one here is a variable resistor. Now all I'm doing is just stating the name of that component. I'm not writing a full sentence. So that's my first mark. Why is it needed in the circuit? Well, that's kind of explaining a bit more, so I'm just going to leave that. Part B, we've got a graph like this. It's an IV graph. Look at the graph. What is a component? So the one that has a straight line is going to be a resistor. There might be one that's kind of flat and then it comes up at the end, and that's a diode. This kind of curvy S is a filament bulb or a lamp. Now, again, I wouldn't say that that's a full sentence. That's just a statement of what it is. But again, that's enough to get us the next point. We then go on to a describing thing, so I'm just going to ignore that. But we've got a calculate. Calculation's brilliant. You've been given an equation sheet for the exam. You should just remember a lot of the equations anyway off by heart if you understand the subject. We want to calculate the potential difference across component X, which is the one in the diagram here. We know it's got a resistance of 16 ohms and a current of 0.25. And it even says which equation to use. We say that V equals IR, which is equal to 0.25 times 16. So a quarter of 16 is just equal to 4. And I'm going to give my answer as 4.0 volts for 2 marks. 2 significant figures like that raw data. We want to calculate the power. There's a couple of ways we could do this, but we can say that P is equal to I squared R. So that's going to be equal to 0.25 squared times the resistance of 16. So a quarter of a quarter is a 16th. Times 16 is just going to be equal to 1. So again, that's going to be equal to 1.0 to 2 significant figures, watts. So there we go. Another 5 marks from those couple of questions. We then have a description. Going to leave that, but we're going to draw the shape of the field around the wire that's got a current through it. Now for this, I know I've said no calculators, but I am going to be using one of these. Okay, it's really important if you can. Okay, this is not. Okay, I've not set this up well, have I? Basically, a compass is really important if it comes to kind of sketching circles. I'm going to draw a circle there. I'm going to draw another circle a bit further out. And this is just going to really help me as I draw my diagram. So a couple of light lines there, not the best. So this is the wire in the middle. I'm going to just trace over the top of this so that if it was a real exam and it was being scanned in, all of the stuff that I write on this is definitely going to be scanned in when it comes to marking. Okay, so we've got a roughly circular path there. Draw the shape of the field found around the wire. Okay, so if the current's going that way, the current is going into the paper. So I'm just going to put a little cross in the middle, and that means it's going to be going clockwise around it. Okay, so I've got my arrows there to show that we've got basically the current is going into the paper, and therefore my magnetic field is going to be going clockwise. So a couple more marks for that. Not the neatest, but I think we get the idea. Ignore that one. Explain, write that. Okay, here we've got a calculation. Calculate the charge that flows past a point in the circuit with a current of 5 amps for 5 minutes. So the charge flow is the total charge transferred is going to be equal to the current multiplied by the time, which is 5.0 amps times 5 minutes. That's times 5 times 60. So we've got 5 times 300, and that's just equal to 1500. So my answer for this would be 1500 coulombs for 4 marks. Equation, converting the time to seconds, putting the numbers in, and getting an appropriate answer. Describe the pattern, identify the mistakes, going to ignore those, identify the error, blah, blah. Okay, so this one here, nothing I can do there that doesn't involve writing a sentence, so I'm just going to ignore all of that. But our kind of score's pretty good at the moment. Plot the variables on the graph, some have been done for you. So we've got 0, 2, 4, 6, we're going to have to do 8, 10 and 12. Sometimes, again, it's useful to do this in pencil beforehand, just in case you make a mistake, you can always rub it out. So when we've got 8, we've got 0.04. When we're 10, we are at 0.08. And when we're at 12, we're at 0.16. Okay, so I'm just going to go over those in my pen to make sure that they're clearly seen so they can be scanned in. And that's 2 marks just for doing that. Pretty easy. We then have a line of best fit on the graph. Now for this one, a line of best fit doesn't have to be a straight line, and neither does it have to be a continuous curve. This one here, because it's about the behaviour of copper, I'm going to use my ruler, 30 centimetre clear ruler. I'm just going to draw in a straight line where that data appears to be a straight line going through the origin. Okay, so you can see we've got a straight line here, and then I'd put my hand down here and just draw a lovely curve through the rest of the data. I'm just going to go over that in pen. Probably should be doing a ruler for that first bit. So we're going to get something like that. Okay, so that's my line of best fit for another mark. Ignore the description. Calculate the spring constant. It's even given us the equation. Force equals spring constant times extension. So F equals KE. So K is equal to F over E. Now, for the first 6 newtons, we can see here that the force is going to be 6.0. The extension with 6 is going to be 0.03. Okay, so that's the same as 60 over 0.3, or 600 over 3, and 600 over 3 is just equal to 200. Okay, and that's because we've been given the weight in newtons on the y-axis and the extension in meters on the x-axis, so it's going to be newton meters. Calculate the work done in stretching the wire to this. So the elastic potential energy stored is going to be a half KE squared, where that's my extension squared. So that's going to be equal to a half times 200 times to 0.04, 0.04 squared. Okay, now without a calculator, it's a little bit tricky to do that because there's going to be lots of zeros. So I'm going to say that's equal to 4 times 10 to the minus 2 squared. And if we do that, we then find that that's equal to 16 times 10 to the minus 4. But that's not a good way to write it. It's better to say 1.6 times 10 to the minus 3. Okay, so 1.6 times 10 to the minus 3 is equal to 0.0016. And we're going to multiply that, because that's this number over here, by half of 200, which is 100. So if we think about that, we're just going to basically move that decimal point 2 places along to find that this is equal to 0.16. And again, that's a little bit more tricky, but of course, with your calculator, it's easy to do to get that answer. Okay, then let's see what the next question is. Ignore that, a 6 marker. However, don't forget, a 6 marker is really just 3 2-mark questions all in one. So don't think of it as this impossible thing that you can't do. Think about it being a 2-mark question and another 2-mark question and another 2-mark question. Okay, we've now got something where we want to calculate specific latent heat. So E is equal to mL. So therefore L is equal to E over M. Now the energy, it says, is 95 kilojoules. So we're going to convert that to joules to make that 95,000. And we're going to divide that by 0.250. So basically, we're dividing by a quarter, which means we're multiplying by 4. So 95,000 times 4. Well, 2 times 95,000 is 190,000. So we double that again, and that's just going to be equal to 380,000 joules per kilogram. We tend to get big numbers when we're looking at things like specific latent heat. So a few more marks in the bag. We're not going to write down the 2 quantities. I know we can. It's just stating 2 quantities. So what's conserved during an elastic collision? We're going to have kinetic energy is conserved when it's elastic, and it's all nice and bouncy. And also, we're going to conserve momentum. Okay, so that's not a sentence. That's just a couple of statements. Right, we're now going to calculate the momentum of each trolley. The momentum is equal to the mass times the velocity. So the momentum of A is going to be equal to its mass, which is 2 kilograms, times its velocity of 4.2, and that's just equal to 8.4. And I'm going to say that's plus 8.4 kilogram meters per second, because we're looking at a vector quantity, so it has direction. The momentum of glider B, I'm going to call that PB, is equal to its mass, which is 2.5 times its velocity of 2.7. So what's 2.5 times 2.7? That seems a bit more tricky. Well, 2 times 2.7 is 5.4, and half of 2.7 is 1.35. So that's going to be equal to 6.75. So plus 6.75, or I could have said 6.8 kilogram meters per second. Both of those being positive because they both have a positive velocity. Now, they collide and stick together. We're going to calculate the speed of the combined trolleys after the collision. So effectively, the momentum before, which was, I'm going to call that P before, is going to be equal to their total momentum afterwards. Okay. Now, their total momentum before was equal to 8.4 plus 6.75, which is 15.15 kilogram meters per second. Okay. Now, we know that that momentum is going to be equal to their combined mass times their combined velocity. Their combined mass is going to be equal, so the combined mass is going to be 2 plus 2.5, which is 4.5. And that means their combined final speed, v, is equal to their momentum over their mass, which is 15.15 divided by 4.5. Now that one is a little bit more tricky to do in my head. And I know it's going to be between 3 and 4, but I'm not sure the exact number. So I reckon for that one, although it's a 3 marker, I might get a mark for this and a mark for that, but maybe lose that final mark. So maybe for that one, I didn't quite get 3, I just got 2. Okay, we're not going to explain that. It takes 2.2 seconds for the stone to drop from rest and splash in the water. What's the speed when it hits the bottom? So we've got a time of 2.2. The acceleration is due to gravity. It starts from rest and therefore u is 0. So we can say that v minus u over t is equal to a. Or we could rearrange that to say that v is equal to u plus at. Now, of course, if it starts at rest, then u is 0. So its final speed is equal to the acceleration times the time, which was 10 meters per second squared, the acceleration due to gravity, multiplied by 2.2, and that's just equal then to 22. So the answer is 22 meters per second. This one here, we're going to describe the motion, use a free body diagram to help you. So here's my free body diagram. That's the stone. We've got the weight acting down. And basically you've got the weight acting down and there's going to be a drag force acting up and the weight is bigger than the drag. Okay, so again, without actually fully answering the question, I can just draw a free body diagram. I can label the weight down, the drag up, and maybe just say how the weight is bigger than the drag, because they're not going to be balanced because it's not moving at terminal velocity, and that's going to get me another couple of marks. And there we go. That was me just whizzing through the paper quite quickly. But I didn't get there. I did not get my 52 marks. Instead, I got to 50 marks, which I think is pretty good for, maybe spending about 15 minutes doing this. Not using a calculator to check my answers, not writing a single sentence, but getting 50 out of 90 is still 56%, which is still a grade 6, which is still a very, very good mark. Now, of course, I'm sure as you actually saw some of the questions, you could easily get a few marks here and there, and therefore going from a 6 to a 7, or a 7 to an 8, or an 8 to a 9, it doesn't take much more work to actually work on your descriptions and your explanations. So I don't know what that really showed, really, apart from the fact that there are lots of marks available which are relatively easy to get. They don't take a lot of writing, but they do rely on you using the correct equations, and that means you need to know how to use the physics equation sheet. It involves doing some calculations and doing them quickly and checking on your calculator. It's about doing some diagrams and just making sure that the diagrams are accurate and labelled. And of course, if you really want to go from that 7 to an 8 or an 8 to a 9, if you're wanting to get the highest grades, I have many more resources to help you formulate your descriptions and understand the underlying physics and actually work on your explanations. And of course, you can find all of those over at GCSEPhysicsOnline.com, or just follow the links beneath this video for extra resources to help you do really well in your exams coming up. But I hope you found that useful. If you liked it, make sure that you do like and subscribe on YouTube, and there's going to be plenty more content to help you as you're preparing for any exams. Thank you.